jump into looks like it wants to work. It says I'm live there. Okay. Go ahead and close that down. Hello. And we're live. It's a little delayed. Not too bad though. There we go. We're starting to get something that's a little bit better. Slightly higher quality. It says I have 2 people watching. One of them is me. See if we get anyone else here on the live stream. So if you're watching the stream on Canvas, you can go to YouTube, and from YouTube I will be monitoring comments and questions on the chat, which is on the right hand side of the screen, and that way we can have some two-way interaction. Andrew Vu, I see you. You can't hear me. Let me see. I'm going to turn up the volume on my... So as I'm watching the stream and watching your comments on the side, it looks like there's about a 20 or 30 second delay between when I answer something, or when I talk rather, and when you see it on YouTube. So the disadvantage of YouTube is that delay. The advantage, of course, is that it's much higher quality. So I'll do my best to try to answer things, but if I don't answer your comment right away, it's because there is a delay in the YouTube stream. Wait just a couple more seconds here. And you can hear me, but it's really low. Let me see if I can work on that. I'll turn up my mic gain quite a bit here. See if we can get some more audio. That should be a little better. I'll try not to talk too loud and get any clipping on here. I'm curious. I'm going to try one other thing here. Maybe if I do desktop audio up as well, if that gets better audio. Hopefully it should be louder. Hopefully everyone can hear me now. Woo, we got 5 people watching now. Okay, hopefully everyone can hear me. We got our 5 people in on this lecture. So we're going to go ahead and get going. So number systems. This is the last topic we have to go through. And I was just looking at the AP website. They've actually cut off 2 topics, but number systems will likely be something that you might have to deal with. And we'll talk about another reason why it's just a good thing for us to know number systems and understanding number systems for bitwise shifts, which is the last set of basic notation that we have to understand within the Java comparator operators and the built-in operators in Java. So the common bases are base 2. This is what we call binary. Just 2 things. Bi meaning 2, binary. The other common bases are octal, which is 8, and base 10, which is the base that we all know, and hexadecimal, which is 16. And hexadecimal adds in new characters that you've never seen as a number before. And it uses A through F as those new characters to represent numbers, which can get a little confusing because you're using alphabetical representation to represent a number. Let's go ahead and open up bases.java. The example file should be open on the lesson page. So we'll open up bases.java, and this is our basic notation. And actually, Java can handle different bases inside integer. So if we go ahead and run this and we look at the terminal output, we will see that it gives us our base 10 representation of those numbers. So 789 in base 10 is 789. 043, which is base 8, into base 10 is 35. And 0x62 is 98 in decimal. And so Java stores the integer. It doesn't really care what you input as the value. It automatically converts it into its own background information, which is eventually binary. But it can handle those different types of inputs. Putting a leading 0 indicates that it's going to be a base 8 number. And putting the 0 and x, Java can handle this. It understands that that x is not a character, but is in fact an indication that this is a hexadecimal number 62. So what is base 10, really? When we have a number, say 235, what does it mean to have 235? How do we know conceptually what 235 of something is? When you break down each of these digits, so when you break down a 2 Whoops, didn't mean to do that. Oh, let's go back. So when we break down this number, oh, it doesn't give me the drawing tools anymore. No. Okay, sorry, you're just going to have to listen to me talk and point things out. So when you have a number, say 235, the 2 represents 200. Of course, we know this. But how do we break down that even further? Well, it's 2 times 10 to the second power, which is 100. And the 3 in 35 is really 3 times 10 to the first power. And 5 is 5 times 10 to the 0th power. And every single number system follows this pattern, where the first digit, or I should say the rightmost digit, is whatever that number at the digit is, times the base to the 0th power. The next digit is that number times the base to the first power. The third digit is that number times the base to the second power, and it just keeps going up. You just keep adding a power to your base each digit that you move up. So they all convert to this by the same principle, and it actually makes, they all use the same principle, and it's pretty easy to convert from one system to the other, and it's all the math works exactly the same once you're in one system or the other. It doesn't, none of the math that you normally do changes. The only thing that changes is the base where it is. So let's say we're given a number 32 in base 4. Can we convert it to the number in base 10? So if we look at 32, it becomes 3 times 4 to the first power. 3 times 4 to the first power is what? Is 12. Plus 2 to 4 to the 0th power. 4 to the 0th power is 1. So that's 2 times 1, which is 2. So it becomes 12 plus 2. So we see that here, 3 times 4 plus 2, which gives us 14 in base 10. So 32 is 14 in base 10. So if you divide a base 10 number by its new base, you'll get, for each place, the remainder will become the new space for conversion. So given a base 10 number of 70, you convert it to base 5 using these steps. So first you're going to divide 70 by 5, which is going to give you 14 with a remainder of 0. Then you're going to take that 14 and divide it by 5 again, which is going to give you 2. So that moves us one space over, right? We're converting. It's kind of like when we do the modulus thing, we're chopping off a digit each time. By doing this standard integer division, we're able to pull out each digit. So 14 divided by 5 is 2 with a remainder of 4. And then we're able to take 2 divided by 5, we get 0 with a remainder of 2, and that is our last digit. So conversion is actually quite easy. Okay, if it went offline, I just saw that, Andrew. I will record this. It is recording, and I'll post a recording of it as well. So that's how we do a basic conversion, and this is essentially what you do inside of a loop. You'd have to add a modulus in there to do a quick conversion from base 10 to any other number, but that's how you're going to do it. You divide the number, see what the result of that integer division is, do a modulus to find out what the remainder is, and use that remainder to move on to find the next digit. And that is going to be our algorithm for converting any base 10 number to a new base. Any base to any base is essentially this: convert the number you want to convert to base 10. Convert the base 10 result to the new base you want. That's one way to do it. There are more generic ways to do it, and I'll let you guys think about more generic ways to do it. But it involves this kind of process here. You just have to change a few of the parameters. Okay, so binary. Now, I've changed this slide a little bit. Hopefully we're still live here. I've changed up this slide a bit to make sure it's still live. Yes, I think so. So when you see binary, you almost always see it written with leading zeros, meaning that there's zeros in front of the number. You'll see like 0001 or 0010. Those zeros are really there because of just a convention with writing binary, but you don't have to write binary with those leading digits. And so I've given you this chart without the leading zeros, but know that it does or can have those leading zeros in there, and often does. And the leading zeros mean nothing. So if you see a number written as 010 in base 10, that's still just 10, right? Same thing in binary. If you see something 0001 or 0000, that's still just whatever those first digits are. It doesn't change what the value of it is. It just becomes, oh, nope, we're dropping in and out on the live stream. Sorry. Let me make sure, I'm going to be back in 2 seconds. Let me make sure no one's using the heavy house real quick. Okay, I'm back. Oh, hopefully we're... Andrew, so you asked about when converting from any base to base 10, do you modulus the base you want to convert to? Yes, you are going to have to modulus the base you convert to. So if we look back here at this algorithm, the steps show us that we need first 70 divided by 5 equals 14. But then we also have to have the remainder to move on to step 2. So it doesn't show you the modulus here, but that's what you're going to need to do in order to convert. You're going to need to add a modulus step in here, in between these two, in order to find our next value. So the modulus really is what the value of each digit is, whereas the general division gives you the step to move forward, right? Because we're using this 14 to divide this next time, because we haven't found all of what we need to get rid of that 5. So binary, here's how binary works. I talked about leading zeros. The first space, the first digit on the right-hand side in binary is 1 times whatever number that is, which is going to be 1, right? So it's 1 times 1, which is 2 to the 0th, which is 1. The second digit is 2 to the 1. The third digit is 2 to the 2. The fourth digit is 2 to the 3. Just as in base 10, we have a base of 2, and we're just moving the powers of 2 up by 1 each time, starting at 0. So 1, 0 in base 2 is not 10 like in base 10. It's not 10 things. It's 1, 0, which is 2 to the first times 1, and 2 to the 0th times 0. So this sorry, we keep cutting out. I'm trying to monitor the stream on one of these extra laptops I grabbed from school on the side here, and I notice it's cutting in and out. So I'll make sure to post this video so you guys can watch it later. So 1, 0 in binary is really just 2. 1, 1 or 11 in base 10 would just be 3 in binary, because it's 2 times 1 and 1 times 1, which is 3. 1, 0, 0 or 100 in binary is really just 4. 1, 0, 1 is 5. 1, 1, 0 is 6. 1, 1, 1, 1 or 1, 1, 1 is 7, and 1, 0, 0, 0 is 8. And you can continue counting up, filling these up. So you could have 1, 0, 0, 1 here, and that would be 9. And you can count all the way up to 15. So you go 0 to 15 with 4 digits. This is an important thing to remember. 0 to 15 with 4 digits. It's going to become valuable for us in a second. And here's where it is. Base 2 to base 16. So you're going to hear a lot about hexadecimal. And hexadecimal is a really powerful number system in computer science because it is a power of 2. And it is, of course, 2 to the 4, right? 2 to the 4th. And if you actually count 0 in here, so if you have a 0th place, 0, 0, 0, 0, 4 zeros, all the way up to 4 ones, you have 16 different numbers, which is 2 to the 4. So 4 digits in base 2 will give us a 16-digit number. So controlling, going to base 2 and base 16 becomes really easy. And base 8 as well, because base 8 is already a power of 2 as well. So base 2 converts directly. Each 4 digits of base 2, each 4 digits, 0, 1, 0, 1, 1, equals B in hexadecimal, which is 11. And 1010 is A in hexadecimal. So when we're counting in base 10, we have to think about the fact that 0 to 9 gets us 10 digits. Those are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10 separate numbers. But in hexadecimal, we're looking for 16 numbers. And we don't have 16 numbers or 16 symbols that generally represent numbers for us in our standard number system because we are base 10 in most of the math that we do, 0 through 9. So what they decided to do, because I don't know exactly why, but it's my guess is it has to do with the way that ASCII works, is they decided to use the first 5 letters of, or sorry, the first 6 letters of the alphabet, so A, B, C, D, E, and F in capital letters, to represent the numbers 10, 11, 12, 13, 14, and 15. So when you see the number A in hexadecimal, it really means 10 times whatever that digit place is. And B is really 11 times whatever that digit place is. And we can see that in the representation here of binary 10 and 11. Down here, again, we see that it's just like any other number system where each one of these groupings of 4 is now going to control a digit. And our digit in this case is going to be 1 times 16 squared, 4 times 16, and 10 times 16 to the 0th. So if we think about that, if we think about that as base 10 numbers, let's do the math really quick. Base 10 numbers, 10 times 16 to the first power, because this is the first digit, right? A. So it's going to be 16 times 10. That's 160. Plus 11 times 16 to the 0th power, which is just going to be 11 times 1, which is going to be 11. So this number, AB, in base 10, really is 171. 160, 10 times 16, plus 11, 171. Let's take a look at our next number, 14A. So 14A is going to be 1 times the third digit. Now your temptation is going to think of it as 1 times 160, but it's not 160. It's not 10 squared, it's 16 squared. And 16 squared is 256. So it's going to be 1 times 256 plus 4 times 16, which is 64, plus 10 times 16 to the 0, which is 10 times 1. So 256 plus 64 plus 10. My math is right. That should be 330. You can check me on that. Also, if you really want to have some fun with this and you're not sure what the math is, and a great way to check yourself on the assignments, if you open up your calculator, standard calculator on Windows, and you go to this little burger symbol here, there's a programmer section. And the programmer section has different base systems. So if I click on hexadecimal base number system right here, and I go ahead and type in 14A, I look at decimal, DEC, and there it is, 330. And I can even click on that and do my math again in decimal. And it even shows me that binary. The binary is correct. 001, 0100, 1010. Really easy way. I can even do bit shifts. This is a really cool thing. You can click on individual binary numbers here, and it shows you what this is. This is the 64-bit place, hexadecimal, octal, and decimal. Shows you what those numbers are. We'll talk about bitwise shifts in a moment. So there's a direct conversion from base 2 to base 16. Oh, it went backwards. And also from base 2 to base 8. The difference is in base 16, in hexadecimal, we're using 4 digits of 1s and 0s to convert to base 16 from decimal, or from binary, sorry. And in octal, we're using 3 digits of binary to control each digit in octal. So let's take a look at what these numbers would be in decimal so we can get a little better understanding of what this is and how these numbers convert. So 101 in binary is 5, and 011 in binary is 3. So our direct conversion to base 8 is 53. We can do the same type of math that we did before. So our first digit here to the right is going to be 3 times 8 to the 0th power. So 3 times 1, which is going to give us 3, plus 5 times 8 to the first power. So 5 times 8 is going to be 40, which 40 plus 3, 53 in base 8 is 43 in base 10. One of the nice things of any base smaller than 10 is that, generally speaking, the last digit is going to match whatever your base 10 is. Let's take a look at the next one, 127 in base 8. Something also to notice about patterns in bases is that anything smaller than base 10, you're going to use a normal number set. It's going to look like a normal number. But this last digit will never get bigger than 8 in this case. And so we can use a normal number set because our normal number set goes up to 9. Whereas, remember, in hexadecimal, we had to use a larger and extend the character set in order to get our hexadecimal numbers. So let's convert this into our base 10. And we're going to work from right to left. That's a much better, more consistent way to work to make sure that we have all of our numbers in the correct position and all of our powers correctly ordered. So first is 7 times 8 to the 0th power, which is 1, and we're going to get 7. So we're going to have 7 in there. Our next number is going to be 2, 0, 1, 0. 2 times 8 to the first power, so 7 plus 16 in this case. And lastly, we're going to have 1 times 8 squared, so 1 times 64. So this one again works out really nice, where we have 64 plus 16, that gives us 80, plus 7 is going to be 87. So 127 in base 8 is 87 in base 10. So go ahead and open up javabase.java. So in javabase.java, we can see that we have a string here, and it changes our number based on this second new parameter. We've never had this parameter before in Parson. We've never dealt with this before. But that gives us a new base number. The standard base is, of course, base 10. So the standard number is base 10. And in this case, we can put in a new base to go through this. Yeah, let me go ahead and review the math one more time for you, Andrew. I'll go ahead and open up Notepad here. Okay, I'm going to go through the base 8 case here. We'll make nice big text so you can see what's going on. So if we have the number 53 base 8, this number needs to be converted to our new number, which is base 10. If we want to convert to base 8, convert to base 10. What we're going to do is we're going to take each digit at once and multiply it by the power. So 53, we're first going to take the 3. It becomes 3 times 8 to the 0th power. 8 to the 0, which is going to give us 3. And we're going to add to that 5 times 8 to the 1st power. Which will give us a value of 40. When we add these two together, we're going to get a base 10 value of 43. And this is how we do it. So we went backwards, going through each of the digits, taking each digit out and multiplying it by the base number to the power, starting at 0 and moving up by 1 each digit we move over to the left. Let's take a look at the next example of 127. So 127 base 8, convert it to base 10. So we're going to work it the same way from right to left. So it's going to start out with 7 times 8 to the 0th power, which is going to give us 7. And then we're going to add to that 2 times 8 to the 1st power, which is going to give us 16. And we're going to add to that 1 times, oops, not a capital X, 8 to the 2nd power, which is going to give us 64. So in base 10, our number will be 64 plus 16 plus 7. So 64 and 16 is 80, so this becomes 87. (43) base 10 to base 2. Okay, let me do 43 base 10 to base 2. Let's try that. Okay, so the steps that we go through in each of this is the same steps that we go through. Let's look at our algorithm that we have here. So this is our base 10 to any base algorithm. So we're going to take 43, we're going to divide it by 2, and we're going to need to look for 2 answers. We're first going to need to look for our result and our remainder. So our remainder becomes our digit. In this case, dividing a number by 2, we're only going to be able to get a number of 0 to 1. It'll be 0 or 1. So 43 divided by 2, the closest thing we can divide evenly is 42, which is going to give us a result of 21, with a remainder of 1. So this is our first digit. Then we're going to take our result number and we're going to take that and divide it by 2 again, basically until we're not able to divide by 2 anymore. So 21 divided by 2 is going to give us 10, with again a remainder of 1. And then we're going to have 10 divided by 2, which is going to give us 5. And we have a remainder of 0. And we're going to go through this again. since we still have a result that's bigger than 2, we're going to keep going. We're going to say 5 divided by 2. That's going to give us 2 with, again, a remainder of 1. And we're going to have 2 divided by 2, which is going to give us 1 with a remainder of 0. And finally, we're going to have 1 divided by 2, give us 0, and a remainder of 1. So here we are. This is our result. If we read from the bottom up, this is our number in binary that represents 43. So we read from the bottom up, we're going to get a number of 101011. And we can do the conversion back to check this. So let's do the conversion back to get this. The conversion back is, we go back the other way. So 1 times 2 to the 0th power. 1 times 2 to the 0, which gives us 1, plus 1 times 2 to the 1, which gives us 2, plus 0 times 2 to the squared gives us 0, plus 1 times 2 cubed, which gives us 8, plus 0 times 2 to the 4th, which gives us 0, plus 1 times 2 to the 5th, which gives us 32. And that equals 32 plus 8 plus 3 in base 10 is 43. And that's how we know we did it right, because we were able to go back and forth. Zoom. Oh, that zoomed out. And this digit, again, if you read up, 0, 1, or 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1. And we look here in our 1, 0, 1, 0, 1, 1. So this algorithm right here is basically the algorithm we did here, but in reverse. And this is how you do quick conversion. Let's talk about the quick conversion to base 8 from octal, or to octal from base 8. If you look here closely, these 3 digits, 2 to the 0, 2 to the 1, and 2 squared. 2 squared controls the 4's digit. So this is, if you add up from 0, 0, 0 to 1, 1, 1, that is 8 different combinations. There are 8 different ways you can have zeros and ones organized in 3 different spots. So if we know each one of these groupings of 3, we can actually do a quick conversion. So let's take a look at this. If we split this in 3 and work as this in octal instead of in binary. So we know that 0, 1, 1 in octal is going to be 2 to the 1st plus 2 to the 1, which is going to give us this is going to give us 3. So this is base 8. Now, 101 is going to give us 5 in base 8, because that's 1 times 2 squared, which is 4, plus 1, which is going to be a total of 5. So since we have 5 and 3 controlling by those 2 digits, this is automatically what our number is. That's all we have to do, is just change the grouping positions to find our values. We can do this again in base 16. So let's do this in base 16. Let's take this number and group it differently. The only difference between converting from binary to base 8 is how you group it. So our basic number again is 101011. So instead of grouping it by 3s as we did for base 8, we're going to group it by 4s. So we take the first 4 digits and move those over. And this one, just to make it look symmetrical, we're going to put 2 leading zeros there to make our calculations a little bit easier. So we take these first sets of numbers and we take a look at what their values are in base 16. So 1011 is going to be 8 plus 2 plus 1. So this is going to be the value of 11. And if we look back at our conversion chart here over on, where is it? This slide right here. 11 is, in fact, B. So this is B. And if we look at this digit, we have 0 times 1 and 1 times 2, which is going to give us 2. So in our 2 different number systems, we have, let's see if I can make this look a little bit neater. 53 is going to be our number in base 8, and 2b will be our number in base 16. And 43 is our number in base 10, and 101011 is our number in binary. All of them represent the same value. They just have a different way of being represented in our number base systems. Hopefully that clears it up a little bit. So the javabase.java file is able to convert and do some quick conversions for you. So by saying parse int and giving it a base number, it automatically converts it to the standard integer base. And when you print it out, it's going to print it out in base 10, because that's what we as humans can do mental math the most easily with. You can convert it to a different value on the printout. So just like the parse int can take a new base number, like we did on line 1 here of 6, let me show you in VS Code here. So just like we did on line 11 here, let me make sure this is big enough that you guys can see. Zoom in a little bit more. We'll get rid of this guy. Oops. Let me get rid of the Explorer here. Ah, there we go. So if we look at line 11, we're able to take it in as a new base. So we're converting automatically as we take in this integer value. We're automatically taking it in as a new base number. So 324 as base 6. Because we have this second parameter. We're then able to also print using new values. So using new bases. So I can print things in new bases. Here, I'm taking the number 90 and I'm printing it as a string in binary. So all three of the last lines are going to represent the number 90 as we know it in decimal. But it's going to be that number now in these different bases from binary, octal, and hexadecimal. So if we go ahead and run this, so 10, 11, 010, 132, and 5A down here at the bottom, those are all the number 90 as we know it in decimal, but represented in the different base values. 324 in base 6 is 124 in base 10. 124 in base 10 is 7C in base 16. We can check all of these values using our programmer calculator. If we clear all of this, we can go to decimal, make sure we're working on the decimal setting. We can type in 90. And 90, we look hexadecimal there, it says 5A. And in octal, it says 132. Yay, Java's running right. And our computer calculator and Java match up. And even binary, 0, 1, 0, 1, 1, 0, 1, 0 is the same as we get from Java. Adding and subtracting in any base, just like we do with base 10. So the tricky thing to remember when doing math in different bases is that when you carry numbers, it's a new value to carry those numbers. So you don't carry the numbers at the same place. So in base 8, we have to carry anything greater than 7 over to the next digit place, right? So 5 plus 5 here in base 10 should be 0, right? 5 plus 5 is 10, so we'd put a 0 and we'd carry the 1 over to that next digits place. In base 8, 5 plus 5 is 10. But 10 is really 12 in base 8, right? Because 10 is 2 more than our 8. So we're moving from 7, and then we go 10, 11, 12, which is what we would put. So we'd put the 2 down and carry the 1 over into the next digits place. The next digits place, we have 4 plus 4, which is 8. 8 we shouldn't have the base number 8. We should see it goes 7 and then 0. So we're going to move, that should be a 0 plus the 1 that we just carried from the last column. We get 1 and we carry another 1 over. 1 plus 3 is 4 plus the 1 that we just carried is 5. So this is how we do our basic math. Same thing with base 12 or subtraction in base 9. You just have to be really careful about making sure that you're carrying things in the right order and at the right value. Binary operators. Okay, so these are the last sets of operators that we have to worry about in Java. And if you'll notice, the first two operators here, the AND operator and the vertical pipe operator, are very similar to something we've already used, the double AND and the double pipe, which is the reason why we use double AND and double pipe is because the single AND, ampersand, and the single pipe is already used for binary operators. What binary operators allow us to do is actually to work at a binary digit level to manipulate data at its smallest and honestly its fastest way to manipulate data. Let's take a look at how these work. So operator precedence, I've shown you this set of operators a bunch of times already, but this is an important thing to remember. We've learned everything except for these binary operators, the bitwise shifts, and the bitwise and, XOR, and OR. We'll talk about what XOR is, kind of a cool operator. So open bitwise and, bitwise OR, and bitwise XOR, and let's play with those a little bit. Sorry, sometimes I breathe through my nose and it becomes really loud on here. I apologize if that's annoying. I will try to stop that. So let's open up bitwise and take a look at that. So bitwise and works on data at the bit level. And it compares, just like a regular AND does, whether or not two things are true. But what it does is it stacks the two bits. So it looks at them kind of vertically, and it treats a 1 as a true and a 0 as a false. And it goes through and it reads the digits, looking to see how each digit is true or false. So in this case, our first place digit is true and false. Let's run this and see what the output is. So it's true and false, right? And true and false is going to be false, right? In order for and to work, both things have to be true. Same thing with the next three digits. The first three are false, which means it's automatically going to be false. So you're going to have 4 zeros because this pair of digits is false, this pair of digits is false, this pair of digits is false, and this pair of digits is false. Everything is false, which is going to give us a bitwise and of 0. Everything is going to be 0. Let's take a look at bitwise OR. So in bitwise OR, we're now going to be using the OR operator just like we do in a standard OR Boolean statement, where it's going to check for whether or not a bit is on or off. On being 1 or off being 0. True being 1, false being 0. And if either one of the bits is true, it's going to put that bit in as true. So our first pair of bits, 1 and 0, there is something true there, so it's going to put 1. 0 and 1, something's true, it's going to put that there. 0 and 1, again, something's true, it's going to put it there. 0 and 1 again, and it's going to put something there. So we're going to have 4 1s, 4 things that are true. 4 1s in binary is 15. So our expected output when we run this should be 15, and there we go. 8 and 7 in a bitwise OR is 15. Let's take a look at XOR. Oops, not class. XOR.java. Okay, so XOR is kind of interesting in that XOR checks if it's kind of like OR in that if one of them is true, good. But if both of them are true, it's not so good. So if one is true, it's true. If both are true or both are false, then it's false. Let's take a look at this, and we'll play with this just a little bit so that we can see what the outcomes are. So you should have this open so you can play and kind of learn what this is. So in this case, 1 0 0 0 and 0 1 1 1, so 8 and 7, should give us the same output as a standard OR. And it does. 8 and 7 gives us the same output as an OR. But let's go ahead and change int 1 to 9. And that's going to give us 0, 1, 0, and it's going to add a 1 to this place right here. And let's see what happens. Because in an OR statement, this would still be true. But let's see what the value is. Let's run it. And in this case, we get 14, which is 1 less than 15. So because the last two digits were both true, it actually said false. So a XOR only takes it if 1 is true and only 1 is true. We can test this again by putting this back to 8. So our last digit is 0. And we're going to reduce 2 by 1 as well. Put it to 6, which will reduce this last digit by 0. And let's take a look at what our output of that is. We're going to run it. And we get the same output. So this is 8 and 6 here. Let me run it again just so it's clear here. So 9 and 7 gave us 14, and 8 and 6 also gave us 14. Because since the last digit is already false, it's going to stay false. So it's kind of tricky in that it's going to pick 1 if there's 1's already there. If there's 0's there, it's going to stay 0. And if there's 2 1's, it's going to stay 0. This can be a very useful tool, but it's not something we're going to run across a whole lot. And it's actually not something that's tested on the AP exam. But it is something that we want to know because it is part of our Java operator set, and we want to at least have the full Java operator set, so at least you know what they are. You don't have to know how to use all of them. Let's get back to the PowerPoint, and it'll walk us through each of these. So just as we said, the AND checks to see if both digits are true. So if both digits are true, both digits are 1, then it's going to move the 1 down into the result. Since none of these digits have a 1 in both columns, it's going to not put a 1 there at all, and our output is 0. Bitwise OR, same thing. It's going to look for a 1 in either column because it's an OR. So if there's 1 or 0 in either space, as long as there's a 1 somewhere in that column, it's going to put 1. And XOR is going to work basically the same. We just talked about it though, but it's going to look for 1 or 0 in either column, but if it sees 2 1's, it's going to put a 0. And if it sees 2 0's, it's going to put 0. Open Shift Left and Shift Right. So I've just opened up Shift Left. And what it does is on a bitwise level, it moves a number, an integer, over by 1, in this case, 1 position. So it's going to bitwise move by 1, I guess not decimal place, but it's going to move it over by 1 digit. So a bitwise move from 8 is going to be 16. Let's take a look at why that is. That's because 8 in binary is going to be 1 0 0 0, right? Which is 1 times 2 to the 3 power and plus nothing else, because 8 is just 2 to the 3. Now, if we shift it, if we shift by 1 to the left, that's going to add an extra 0 to the right. Because it takes the whole number and shifts it over by 1 to the left. And that's all it is. And we could put a different value in here. For 1, we can move it over by 2. if we move this over by 2, we just add another 0 on here to shift it over one more time, and now it becomes 2 to the 5th power, which would give us 32. 2 to the 5th. All it does, I'm sure you can figure out pretty quickly what shift right does. It does the same thing, but in the other direction. Okay, but it can get a little weird with negative numbers, because negative numbers, if you recall, aren't necessarily like we think of negative numbers. There's no negative sign in the memory. So let's run this and see what happens. Let's see what it does. So 8 shift 1 to the right does 4, which is what we think of it should do. Now, -9 with 3 arrows is going to do something a little bit different. And I've actually never seen that notation, so let's go Google it. Let's say Java bitwise shift 3 arrows. Geeks for Geeks, almost always a good source. It's an unsigned right shift. So this gets into the idea of what a signed integer and what an unsigned integer is. And I'm fairly confident that the difference between signed integers and unsigned integers is not going to be on the AP exam. However, it is something that we can get a decent idea of what it does. So a signed integer, so this is an unsigned with a G. So an unsigned integer is an integer that doesn't have a negative. And this can be powerful for us because sometimes it will help us with math and help us to move things around. But in most of the math that we do want to have negative numbers because we want to be able to do subtraction and things like that and not have to do bitwise shifts in order to do that kind of math. So Java as an integer has that negative 2 billion some odd number up to positive 2 billion and some odd number. But we can have unsigned shifts. And the basic way that Java works is there's a bit at the front of a number that works as the kind of the indicator that this is a negative number. So if the very first bit at the beginning of a really long string of ones and zeros that represents our integers in memory, if that very first bit is turned on, that means it's a negative number. And that very first bit is going to sit at 2 to the 31st power. If we do an unsigned shift, it's going to move that 2 over to the 30th power, which is going to give us our 2 billionth. If we do a bitwise shift without moving that first digit, which is what a normal 2 arrows does, it's going to give us -5. Let's see if we can replicate this on the calculator. So on our programming calculator here, let's go ahead and enter, let's clear this. We're going to make sure we're working in decimal, and we're going to say -9. And we're going to make that a -9. So if we look at -9 in binary here, it gives us a really weird number. And if we do an arithmetic shift it by, let's see, they asked by shift by 1, what do we get? We get 5. And it's going to do a standard shift here. Let's see our bitwise. Let's try again. Let's clear this. So 9 negative, and we're going to do a rightward shift. Oh, calculator's freaking out. 9 negative, rightward shift by 1, negative 5. There we go. I think I hit leftward shift. So it works kind of the opposite of our normal numbers. And it allows us to move those numbers and shift them over. In this case, it's storing, instead of having an indicator value at the very beginning, it's filling everything with 1s and moving it over. Again, way beyond what we really need to know and understand for the AP exam. But it gives you a little bit of an insight into how these number systems work and how we're able to do relatively complex math, and in fact very complex math, using some of these shifts. And this is how the computer actually does it at the CPU level. This is how all math is done at the CPU level, is doing these types of shifts, additions, ORs, and XORs at the CPU logic level. This is how all math is computed. All right, let's get these last few sides done so we can get out of here. So shift-wise left moves everything over to the left as it shows you. And our last slide, 24 of 24, we have our shift to the right. And again, the triple one is an unsigned shift, which is going to move everything over. And I don't think our calculator can do an unsigned shift. Let me see if the calculator can do that. Bit shift. Let's try rotate circular shift. That might do it. Let's see, 9 times a negative number, 1. Oops, clear. 9 shift 1 on a circular shift equals 0. No, that didn't do it. Let's try logical shift. 9 negative number shift 1. Okay, it did do it, but it's using the wrong, it's using a larger number system. It's using a base 64 number system instead of our base 32 number system. So this number is 9 quadrillion instead of the 2 billion that we get out here, but it uses the same logic in that it's using the unsigned int. And you see that very first digit right there flipped over from 1 to 0, and that's what got us to our giant, huge, massive number. If we click on the binary option here on the calculator, and we go over to this little, we have the normal number keypad, and then we have the binary keypad. If we flip that first digit on, look at that, decimal becomes -5 again. So just by clicking that very first decimal, it takes us from a massive, huge number to a small negative number. And if we start kind of randomly clicking around on these digits, you can do this. I highly recommend that you take some time to poke around on this calculator in the programmer mode and use this as a way to check your values for these labs. Well, once we get into the labs for this. I realize this is the end of the video, and we've lost some people watching now. We're 74 minutes into it. I'm sorry for so long, but just a couple quick notes on the AP exam. We'll make sure to post things up on Canvas as well. So the AP has, if you look at my previous announcement a little while back with a link to the AP site, on that link, they've posted what they're changing about the AP exam. And it's going to change a little bit about how we go forward in this class. Number one, it's probably going to be a take-home exam, or like 90% sure it's going to be a take-home exam. It looks like the earliest we'll get back into school is May 1st, and our scheduled exam date is May 8th. So it's unlikely that we will be able to actually take the exam as we schedule to do it. And like May 1st is the absolute earliest. So it's going to be a take-home exam. It's going to be an online take-home exam for the most part. The other thing is that there will be no FRQ. So for some of you, that's good news because we struggle with the FRQs. For some of you, that will not be so great because the FRQs are where you can make up a lot of points. And the last part is that units 8 through 10 will not be on the exam. And if I remember correctly, that should be... Here, hold on just a sec. So I'm just making sure I'm right here. I don't want to speak out of turn. So that means that there is no 2D arrays. No inheritance. And no recursion. This is great news. The bad news about this is that it's likely going to be a very difficult exam. They say it's only going to be, I think it's 45 questions. I can't remember if they said it's 45 questions or 45 minutes. I doubt it's 45 minutes. Probably 45 questions. There's going to be 45 very, very difficult questions, and they're going to lock down on cheating really hard, and they're going to be examining people's answers and their tests. I don't know exactly how it's going to work yet. It's probably going to be somewhere in the College Board AP Classroom thing that we logged into way, 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 way back in the beginning of the semester. But that's what we're going to be doing for the AP exam. All right, I've already lost another one of you. Correct, Andrew. APCS won't have an FRQ as far as I am aware. I will double check and keep you guys posted as soon as I know. But as of right now, there's no FRQ. It's only multiple choice. Take home, multiple choice. Okay, this is signing off. I will make sure this should be posted, and I'll make sure that it has the full stream. I will see you guys tomorrow for lab help. I will be streaming back here. Unless there's any other questions. I don't see anything popping up. I'll see you guys later.